Okay, in the rest of this session, I'll spend 30, hopefully less, 30 minutes or hopefully less, talking about two things: a programming language, a domain-specific programming language called P4, and an API called P4Runtime, a gRPC-based API. Finally, we'll spend the rest of the session doing some hands-on exercises to get more of a practical understanding of these two things. So before describing P4, it's useful to clarify terminology. I'll talk a lot about pipelines, packet processing pipelines, and what I mean by that is the following. If you take one of these two devices, a switch or a network interface card, these devices usually include hardware like silicon, like an ASIC or an FPGA chip or an NPU or even a CPU that is usually designed or abstracted and programmed in the case of a CPU to process packets in a pipeline fashion. So the idea is that you have a pipeline of match action tables, the same match action tables that were made popular, at least in the networking field, by OpenFlow. And these are arranged in sequence. So that's what we define a pipeline of match action tables. P4 is essentially a programming language to define these pipelines. It's a programming language that can describe things like protocol headers, these lookup tables, the actions that can be executed in these tables, things like counters, and et cetera. It can be used to describe both very high-speed devices like ASIC-based or FPGA, as well as lower ones, like, for example, a software switch or virtual switch running inside Linux. The important thing is that P4 is good not only for programmable switches, but also for fixed function ones. And the reason is that by formally specifying the pipeline, we are defining a contract between the control plane and the data plane on the actual capabilities that are supported by the data plane. So this is the workflow you will find out by working with P4. So the idea is that you have a P4 program, you run this program through a compiler that is usually provided by your switch vendor. And the compiler, what it does, it generates a configuration that realizes this given pipeline on a target, like an ASIC. And the ASIC, in this case, could be programmable or fixed function. There are two versions of the language, P4.14 and P4.16. P4.14 is the original version. It assumed, because it's the first version, it had some limitations. First of all, it assumes specific device capabilities, so it was good only for specific targets, mostly programmable switches. There is an evolution to that, which is called P4.16, which is the most recent version of the language, and this is what we'll be using in today's tutorial. This is a more mature and stable language definition. It does not assume any device capabilities, but instead provides this concept of depending on external libraries and architectures that are device-specific, and I'll talk about this in a second. Because of this, it's good for many targets, not just switches, but also network interface cards, not just programmable switches, but also fixed function switches. So today we'll be using P4.16. So to help you think about a programming language and the function of a compiler, it's useful to think of an abstract machine model that we can program using such a language. So in the case of P4, the reference machine model is called PISA. This is a model of a programmable switch, and PISA stands for Protocol-Independent Switch Architecture. This model comprises essentially three blocks. At the very beginning, there is a programmable parser that a programmer can instrument to extract headers from packets. It is usually abstracted as a state machine. So we usually have a start state. For example, we expect to see the Ethernet header. Based on the Ether type, then we move to the next state, let's say IPv4, IPv6, VLAN, and et cetera. Once you extract all the headers, these are processed through a pipeline of generic match action stage unit. When I say generic, I mean that the PISA architecture itself doesn't define any specific capability in the pipeline in terms of, oh, IPv4 is supported, IPv6, VLAN, et cetera. This is just generic memory banks and allows to perform actions on the packets. And we use P4 to actually realize specific instances of match action tables in this pipeline. Finally, there is a deparser that is used to serialize the potentially modified headers that went through the pipeline. serialize this back on the wire. So let's look at an example of how P4 compiler can be used to program a PISA target. So this is similar to the example that Brian showed before, assuming we have a very simple pipeline with a layer 2 bridging table, 2 routing table, one for IPv4 addresses and one for IPv6, and one that does SEL. We can use the P4 compiler to realize this pipeline in our PISA target. In this case, the compiler, the mapping, it's very simple. We are dedicating one generic match action stage unit to each table. But let's assume by looking at how our network works and understanding more the requirements, we realize that we need something like very large IPv4 table and a small IPv6 table, as well as small ACL table. We can define these properties inside our P4 program, and then what our compiler will do will reallocate resources in the ASIC differently to meet this requirement. So this is the case of a programmable switch, but as we said, P4 is good also for the case of fixed function switches. The main difference between programmable and fixed function chips is that in the case of fixed function ASICs, P4 it's used to describe, it's not used to program the ASIC, but it's more tailored to the app's role at the control plane level. The idea is that you can define a logical pipeline in P4 and then map this pipeline to different ASICs that have different physical pipelines. But the good news is that because of this approach, then your control plane applications can be easily portable from one ASIC to the other because they expect to program the same pipeline. And if you have some experience with switching SDKs from different vendors, probably you know what I'm talking about, the pain of like porting a simple like BGP router application from one ASIC vendor to another, for example. Now, what does it mean to write a P4 program? So first of all, the first thing you should ask your switch vendor is to get an architecture definition. So in P4.16, we have this concept of architectures that are essentially P4 files defining which blocks are available in the target, for example, as switching ASICs, which blocks are P4 programmable, and interfaces between each block. Then the role of a P4 program is to provide an implementation of for each one of these blocks. So let's look at an example of an architecture, which is called V1 model. This is a P4.16 architecture that is derived from the previous version of the language, P4.14. As I said, P4.14 assumed specific device capabilities. In P4.16, those capabilities have been extracted to an actual architecture called V1 model. So V1 model defines 7 blocks, 6 of which are P4 programmable, and 1 is fixed function. So the first block is the parser. Then we have a checksum verification block. Then we have an ingress pipeline. Then we have a traffic manager, which is responsible for things like queuing, scheduling, or replicating packets for like multicast application. Then we have an egress pipeline, where the main difference with the ingress one is that the egress pipeline sees packets associated to a specific egress port. So you can define match tables that match on the egress port as well. There is a checksum update block, and finally, we have the parser. This is an example of an architecture. Again, this comes from P4.14, and because of this, it has some limitation. So the community got together, the P4 community, to define other architectures. So another example of a P4 architecture is called PSA, which stands for Portable Switch Architecture. And this is a community-developed architecture, so you can find a specification at this GitHub address. This architecture describes the capabilities that are common to a network switch, where by network switch, we mean a device with at least a dozen ports. It defines 6 programmable P4 blocks plus 2 fixed function blocks. You can see that the order and the structure of the pipeline is slightly different than V1 model. It also defines capabilities that go beyond match action tables. So it defines things like counters, meters, stateful registers, hash functions. So you can do a bit more than V1 model. Other examples of P4 architectures are FlexSci. This is part of the SAI project. The idea here is to define a P4-based architecture that models a Sci-like switch where there are some fixed function blocks abstracting standard networking functionalities like bridging, routing, VLAN handling, things like this. And the idea is to have programmable blocks in between the fixed function ones. And in the green blocks, this is where we can actually use P4 to program some more advanced functionalities. There is also some work inside the P4.org working group to define an architecture for network interface cards. These are slightly different than switches. So network interface cards usually have less ports. They have a different internal architecture when it comes to buffering and queuing. So it's important to have a P4 architecture for that. And there are also proprietary architectures like the Barefoot to Fino native architecture. And you might be familiar with that if you've been exposed to the Barefoot SDK. So before we move on, let's derive a preliminary takeaway. One of the most common questions I hear when we talk about P4 is, can I implement this or that function using P4? And the answer is, well, it depends, as most answers from engineers. The P4 language per se aims at being flexible enough to describe any forwarding behavior that can be abstracted with match action tables, independently of the headers you can match on, the type of actions you can perform, things like that. But the specific capabilities depend on the architecture. So the answer is usually, well, it depends on the architecture you're using. If the architecture supports the capabilities you need in your P4 program, then you can implement that function. So things like doing ternary match versus longest prefix match or exact match, or supporting things like ECMP or stateful memories to implement counters, that all depends on the architecture definition. The second question is, once I have a P4 program working on a given target, can I execute the same program on a different switch from a different vendor? The answer is more complex, a bit more complex than that, but usually starts yes, if that vendor provides you with a P4 compiler for the specific architecture. So the first takeaway we should derive from this is that architectures enable portability of P4 programs across different hardware and software targets. So again, it's fundamental before starting to think how to write a P4 program, understanding the architecture we want to write our P4 program for. And in the exercise, there will be a bit more of explanation of this. So this is an example of a P4 program written for the V1 model architecture. Again, this is P4.16. If you look at the very top, we usually start by importing the standard P4 core library. This defines the very basic primitives of the language. Then we include the architecture definition, in this case, V1 model. And now let's look at the bottom. At the very bottom, the last thing you usually do at the end of the P4 program is an instantiation of the switch, where you provide an implementation of all the P4 programmable blocks I was talking about before. And this implementation of these blocks are defined in the P4 program itself. So we have an implementation for the parser, we have an implementation for the checksum verification block, an implementation for the ingress pipeline, egress pipeline, checksum update, and the deparser. And again, we are implementing the 6 programmable blocks because V1 model requires us to do that. If you're using a different architecture, you might to provide an implementation for a different number and type of blocks. This is an example of a P4 program, or at least some small pieces, snippets from a P4 program implementing a standard IPv4 routing table. In this case, we have header definitions for 2 headers, the Ethernet header with its source address, with its MAC address and ether type. We also specify the bit width of the fields. We have also a definition of the IPv4 header with its fields. And then in the ingress pipeline implementation, we have a table definition for our routing table, in this case, matching only on the IPv4 destination address. The type of match in this case is longest prefix match. This is usually what it's used for routing tables. And this table uses two actions, allows the control plane to insert entries using two different actions, either drop or set next stop, where setting the next stop will perform the following operations in the packet. So setting the destination address to the given one and decrementing the TTL. Now, if you look carefully, you might find there's a bug in this P4 program. Can anyone spot what the bug is? It's very simple. We're not setting the Ethernet source address. So a router usually updates both MAC addresses when routing packets. This is the beauty of P4. You find a bug in your pipeline implementation, you fix your P4 program, you recompile the P4 program, and you test it, and hopefully the bug is fixed. You don't have to go through a ASIC design cycle to fix this issue, which can usually take years. So now that we've defined our P4 program, in this case implementing a simple IPv4 router, it's important to specify and be clear about the fact that P4 specified the data plane packet processing pipeline. But then to have this router working in a real network, we also need a control plane. P4 does not define the control plane. We use different mechanisms to implement the control plane. And this can be a standard BGP or SPF control plane. What we need in this case is an API to insert table entries in the table we define using P4. So to summarize the workflow, including the control plane, we have to write a P4 program to use P4 with a programmable or fixed function switch. The first thing we need is to get, first of all, a switch from our switch vendor, then get a P4 compiler and architecture definition. Then we can write a P4 program against this architecture definition and compile it. This will produce some target-specific configuration that we can push to our switch. And finally, we can implement a control plane to modify at runtime the content of our tables. In this case, the API we use for the control plane is called P4Runtime. So before we move on to P4Runtime, is there any question related to the P4 language? I want to mention that the goal of this tutorial is not to give you it's not a tutorial of the language per se. In the first exercise, you will be given already some P4 starter code that is commented enough to get you to give an understanding of what's going on. But definitely, if you're more interested in the language per se, I suggest we can give you some pointers at the end. So this is just to give you an overview of the main capabilities and concepts. So talking about P4Runtime, again, P4Runtime is a runtime, is an API for runtime control of P4-defined data planes. It was released on January of this year, 2019. It's an open source specification. It's based on some work that started between Google and Barefoot Networks in mid-2016. It includes contributions from many industry professionals, and it's based, the specification, it's hosted on GitHub. The cool thing about the specification is that differently from other SDN APIs, the final specification is actually based on a continuous implementation feedbacks from organizations like Google and ONF. So both Google and ONF are using internally P4Runtime, at least Google for testing. And in the case of ONF, what we did since the very beginning of P4Runtime, we started prototyping the control plane and applications, and we use that to also drive the specification work. So if you're interested in the specification, you can take a look at the links shown in the slides. To give an overview of how P4Runtime works, P4Runtime, again, is based on gRPC, as Brian said. So it's an RPC paradigm, meaning that we have a client and a server. A client issuing RPCs and a server replying to that. In this case, the client is the control plane, so on us, and the server is the data plane. In this case, the data plane agent like m-stratun. The API is based on protobuf, meaning that we can get very efficient wire format, and we can automatically generate code to serialize, deserialize P4Runtime messages in for many languages. It uses gRPC as a transport, again, meaning that we can automatically generate high-performance client-server implementations in many languages. Provides things like pluggable authentication and security, meaning that we don't need to define the security aspect of the protocol in the P4Runtime specification, but we can get it for free by using gRPC. It also supports bidirectional stream channels, meaning that even this is an RPC paradigm, gRPC supports the case where the server sends asynchronous messages to the client. And this is useful to support features like packet-ins, controller packet-ins, where the data plane sends packets to the control plane for further inspection. It is P4 program independent, meaning the DPI supports pushing new P4 programs at runtime to reconfigure the pipeline. And the API is not designed just for SDN and remote control planes, but the same API can also be used to implement a local control plane, so a control plane that runs inside the box, inside the switch. And this can be done with or without gRPC. So gRPC is an option as a transport, but you also have other options, especially if you want to run your control plane inside the box. Maybe these options are a bit more efficient than gRPC. In terms of the main features supported by the P4Runtime, clearly it supports, it's an API to read and write data plane state, like table entries, actions, groups, counters, registers. Like OpenFlow, it supports master-slave arbitration for control plane high availability and fault tolerance. So the idea is that you can have multiple controllers controlling the same switch, one of which is the master instance and the other are slaves in case the master one fails. It also supports this idea of multiple master controllers via role partitioning. This is a very interesting feature, meaning that the idea is that you can have a switch that is controlled by two different control planes responsible of different functionalities. You can have a switch local control plane dealing with things like bridging, and you can have a remote control plane dealing, for example, with routing. And this makes sense because for bridging, the bridging functionality itself needs only visibility from the switch point of view, so it's switch local state, while routing, for example, needs more network level view of things. It might not be the case if you implement expanding tree. But again, the idea is that differently from OpenFlow, where the control plane is assumed as a remote one in all cases, P4Runtime supports this possibility of running switch local control plane as well. It supports flexible and efficient packet I/O. By packet I/O, I mean packet in, packet out in the OpenFlow sense, where a packet in is a packet that is sent by the switch to the controller, again, for further inspection. And a packet out is a packet that is generated by the controller, and it's sent out of a switch port. It's designed around the P4 PSA architecture, but can be extended to support other architectures as well. And it works well with V1 model. I keep mentioning V1 model because we will be using this architecture in the first exercise. So let's talk more in details of how P4Runtime works. So again, the first thing you do when you have a P4 program is to run this P4 program through a compiler. And a compiler, usually a P4 compiler is expected to provide two outputs. The first one is a target-specific binary configuration to realize that pipeline on a given target, like for example an ASIC or an FPGA or a software switch. And the second output is a P4 info file. Well, the P4 info is essentially a schema that specifies the pipeline for runtime control. It's like if you implement a P4 program and then you look at this P4 program from the top, and you see which tables are available, which match fields can be used, which actions are available. So the P4 info doesn't include things like the implementation of the action, so which fields are modified inside that action, but includes information like, for example, which action parameters the control plane needs to provide at runtime, the type of match that is exposed by a table, if it's ternary match or exact match, how many tables are available, things like that. It is based on protobuf, meaning that you can easily serialize and deserialize P4 info files in many you can parse and deparse P4 info files in many programming languages. And it's target independent, meaning that you can use the ideas that given the same P4 program, you should get the same P4 info file independently of the target you're compiling your program for. If it's an ASIC-based switch, if it's an FPGA, the P4 info file should be the same. So to give you an example, if we consider a P4 program similar to the one I showed you before, where we have an IPv4-based routing table that matches on one header field, the IPv4 destination address, and provides one action called IPv4 forward, which takes these two parameters, the MAC destination address and the port. If we run this P4 program through a P4 compiler, we will obtain a P4 info message that looks like this. On the right of the screen, I have an actual output of a P4 compiler, a P4 info file shown in protobuf text format. So what the compiler does, it produces a P4 info that provides a specification of, for example, our table, providing a numeric ID for this table, the associated name, and the list of match fields required by this table. In this case, the IPv4 destination address, the bit width, so the number of bits that must be provided by the control plane when defining a match entry for this table, and the type of match, longest prefix match, meaning that a control plane, when inserting entries into this table, has to provide value, but also a prefix length. So if you want to match on /16, 24, that's how the control plane knows that it can provide a prefix length as well. There's also a specification of the action supported by the table. If you look in the table definition, there is a field called action ref ID. This number is actually a reference to an action that is supported by the table, where we have a specification of the number of parameters that are expected to be provided by the control plane. In this case, the MAC destination address and the bit width of this parameter, and also the port. So let's see an example of a P4Runtime WriteRequest to insert a table entry in our routing table. So again, given a table defined in P4, and given a logical view of a table entry we would like to insert in this table. In this case, we are matching on this IP address, /32, and we are executing this action, the IPv forward action with this MAC address and port. Given a P4 info definition that the control plane has, the control plane can then generate a P4Runtime WriteRequest to write this table entry in the switch. I'm not going into details of the field of the WriteRequest message, but you can see that here we are defining a table entry entity with the same ID that was defined in the P4 info message, the same table ID. We are specifying the match field with the value and the prefix length using the same ID for the IPv4 destination address that was provided in the P4 info. Same thing for the action. We use the same ID, and we use parameters specified using the bit width that was contained in the P4 info, and again, the same IDs. When it comes to pushing down a pipeline configuration, again, we can use P4Runtime to do that. So assuming you find there's a bug in your P4 program, or you want to repurpose your switch to perform a function that is different than routing, you can do so by writing a new P4 program, compiling this P4 program, so obtaining a new P4 info file and a new binary configuration. And then you can use the P4Runtime to push down this new pipeline configuration. In this case, the forwarding pipeline config P4Runtime message takes two inputs, the P4 info file and the P4 device config. And you will see an example of this operation in the first exercise. So to summarize P4Runtime, P4Runtime is an improvement over previous data plane APIs. I didn't talk much about the comparison between OpenFlow and other APIs, but if you have questions, we can talk about this more. But the idea is that P4Runtime realized the vision of OpenFlow 2.0, that is of becoming more protocol independent. If you follow the OpenFlow specification, you might be aware of the fact that OpenFlow 1.0 supported just a few header fields, like 12, if I'm not mistaken. With the different releases of OpenFlow, the number of header fields supported started increasing up to like 40, 50, something like that. And clearly, the idea is that the people working on the OpenFlow specification realized that it was time to separate the two things, the runtime API specification to actually manage forwarding state in a switch, and the specification of the header fields and tables supported by the switch itself. So that's why we say that P4Runtime provides both protocol and pipeline independence. and the protocol supported and pipeline can be formally specified using P4. Again, it's based on protobuf and gRPC, and we saw the benefits of that. And finally, the fundamental piece for the control plane operation is the P4 info file. So the control plane consumes the P4 info file, not the P4 program, and that's because the P4 info is the definition of the contract between the control plane and data plane. So with this, I conclude the introductory part on P4 and P4Runtime. In the next slides, I have an introduction on the first exercise. But before I move on, I want to know if there's any question on P4 and P4Runtime. We can answer that. OK. So if you all got your virtual machine and it's running, then you should be able to work on the first exercise. So in this exercise, we provide you with a P4 program, the P4 program that implements simplified traditional IPv6 router. The P4 program is very well commented, so even if you don't have any experience with the P4 language, if you have basic coding experience and basic networking experience, it should be easy to understand what's going on. We provide some questions inside the exercise about the pipeline capabilities, and you should try to answer those questions to get a better understanding of what this P4 program does. Then you will be asked to compile these P4 programs for BMV2, where BMV2 is a software switch. I'll talk about this in a second, and obtain two outputs. Obtain a JSON file, which is a configuration for the BMV2 packet processing pipeline, and a P4 info file. Then you will be asked to start Mininet, where if you're not familiar with Mininet, is essentially a Linux-based network emulator, that we will use to emulate a simple fabric of 2 leaf, 2 spines using m-stratun BMV2. So this is a version of BMV2 software switch running Stratum. Then you will be asked to run a P4Runtime shell, which is it's not actually a CLI, it's more of a shell, but again, it's a command line utility that you can use to do things like push a pipeline configuration and write table entries in the bridging table of our P4 program. And finally, you will be asked to test connectivity using ping. The tutorial material is all based on Docker, and we use, in this first exercise, we use 4 different tools/Docker containers. We use m-stratun, which is a Docker container which provides Mininet with Stratum BMV2, which is the software switch. This container allows execution of a custom topology script. So in the tutorial files, you will also find a very small Python file that defines a 2x2 topology. We provide a containerized version of the open source P416 compiler called P4C. We provide a container with the interactive P4Runtime shell. And finally, we provide a container with ONOS. But ONOS is not using this exercise. You just run it, and you leave it running, and that will be used in the next exercises. So no need to worry about this. Talking about the starter P4 program that is provided to you in the VM, again, the goal here is to build an IPv6-based leaf-spine data center fabric. So because of this, we want our switches in the fabric to behave like a simplified IPv6 router, meaning that our switches should support functions like bridging for hosts connected to the same subnet, meaning that we expect to see tables that forward packets based on the MAC destination address. And we expect to have a control plane that supports something like host learning to automatically populate our bridging table. We want our routers to support routing based on IPv6 addresses for hosts in different subnets. We want to support ECMP. Again, this is a leaf-spine data center fabric, so we want to be able to load balance traffic to multiple spines. And finally, we want to support controller packet in, packet out. And this is needed for link and host discovery, and will be the goal of the second exercise. We use the same P4 code for both leaves and spines. It's in the tutorial virtual machine at that inside the ng-SDN tutorial directory. As I said before, it's well commented, and it's easy to understand even if you have little or no experience with P4, so don't worry. P4C is the open source front-end compiler. Like many other compiler, as an internal architecture, where we have a front end, a mid end, and a back end. P4C specifies provides an open source front end and mid end, and then we can have multiple backends, which are usually vendor supplied. So if you have a switch from Barefoot Networks or other vendor, if you're trying to program an FPGA, then you should ask your vendor to provide you a backend for the P4C compiler. P4C provides some open source backend, like for BMV2 and eBPF, and we'll be using the BMV2.1, which produces the BMV2 JSON I showed before. BMV2 is a reference P4 switch. It's not aimed at being 100% conformant. Sorry, it's not aimed, the goal here is not performance, so the throughput is usually very low, but the goal here is being 100% conformant with the P4 specification. It's actually a framework to build P4-based switches because it's architecture independent. So you can use BMV2 to specify any P4 architecture. In this case, we use a BMV2 target called Simple Switch with Stratum support, which is an implementation of the V1 model architecture with the Stratum APIs exposed over gRPC. So similar to the V1 model architecture, a Simple Switch defines the same block, so the parser, ingress pipeline, a traffic manager in the middle, egress pipeline, and a deparser. We use P4Runtime to write entries in the different blocks, and the pipeline is actually realized using a JSON file, which is the output of the P4C compiler with the BMV2 backend. We use Stratum BMV2, which is, again, a realization of BMV2 with Stratum on top. Without going into details of this picture, this is the Stratum architecture. What's important to say here is that we use the same implementation of the Stratum APIs that runs on a hardware switch. The only difference is that at the southbound of Stratum, in this case, we have BMV2 Simple Switch, which is attached to virtual interfaces used to emulate links in your network. But the implementation of the top part is the same as the one found in the hardware version, in the version of Stratum for hardware switches. So it's time for you to start working the exercises. The idea is that we provide instructions that you can follow along. And if you need any help, please raise your hand. You can access the instructions in two ways. You can either open this URL on GitHub that provides a nice markdown preview of the instructions, or you can open the instructions in markdown format inside a text editor in your virtual machine. I recommend the first option. It's easier to follow. If you feel stuck, I encourage you to look at the solution folder, even if we provide no solutions for exercise 1, so keep this in mind for the next exercises. Before starting, if you remember to update the dependencies in the tutorial repo directory. So make sure to execute these 3 commands inside the tutorial directory. And again, if you need any help, please feel free to raise your hand and ask questions.